Regula Falsi works on the concept of linear interpolation, and this is shown in the equation for C. Check the second example of determining the roots of a function using the method. Welcome to Numerical Solutions to CE Problems. We are to look for the roots of the function shown, using Regula Falsi method. Accuracy is either convergence or 4 decimal zeros. For us to start the iteration, we need initial values to be limits in the brackets. Since we are looking for all the real roots, we can then assume a wide range of x. Say we start with x equal to -12. Which gives f of x as 36. This is far from the x-axis, but then try other assumptions, say trending to the positive as shown on the table. The values of f of x turns out nearing the x-axis, as the x values approach the positive. Then from the positive x values, f of x results to big values also going far from the x-axis. But then notably, among the f of x values is -0.28172. This is the only negative value cutting through the x-axis. So we found the two roots of the function. The first root is in the first interval. So if we graph the values at x of 0, f of x is 1. Then, with x of 1, f of x is -0.28172. And again, if x is 2, f of x turns to 1.389056. The graph shows that the curve passes through the x-axis on each interval. For now, we know that both roots are positive. Let's look for the root nearest the origin by iteration with Regula Falsi. Before the procedure, identify the property of A and B. From the graph, A is the left limit, x equal to 0. And at this value, f of x is +1. So we note the sign on A as positive. The right limit is at x of 1, where f of x at this point is negative. Thus, B has the negative sign. This is used to identify where to replace C later on. So let's fill out the table. The left limit is 0, and the right limit is 1. F of A is computed from the table previously as 1, and f of B was also computed as -0.28172. C is computed from the equation for Regula Falsi. So plug in A, B, f of A, and f of B, and have C1 as 0.780203. These values then used to look for f of C, which turns out as -0.15869. To continue to the succeeding iteration, we have to generate the next A and B. By checking the sign of FC, we can identify which limit is replaced by C. For this first iteration, f of C is negative, so C replaces B. Remember that B is the negative limit as we marked earlier. A remains 0, and f of A is also 1. FB is then computed using the new value and turns out as -0.15869. With all four parameters identified, we can compute for C using the equation, where it also results to 0.673347. This value is again used in the function, where f sub C2 is -0.05925. Now for the third iteration, Check the sign of FC, which is still negative. This means that C replaces B again, and A is retained as 0. FA is still 1, and FB now turns to be negative 0.05925. Compute for C3, which should turn out to be 0.635682. And this value gives f of C3, which is negative 0.01874. The fourth iteration starts the same with the FC check. It is still negative, so C replaces B, and A is still 0. F of A is also 1, and f of B is computed as negative 0.01874. C uses the function with the 4 recently solved parameters. C is then equal to 0.623991. F of C4 then is computed using the new value of C, and the result is negative 0.00561. To start the fifth iteration, check the sign of FC. It is still negative, so C replaces B once more. A is retained as 0, and f of A is still 1. FB is then computed as negative 0.00561. Having all these, compute for C, which turns to be 0.620509. By using this value back to the function, we get f of C5 as negative 0.00165. We have 2 decimal zeros at this point, so we are near the end of the iteration. The sixth iteration starts with the sign of f sub C, which is negative, so B becomes 0.620509. A is still 0, and f of A is still 1. But f of B is computed as negative 0.00165. Use these values to have C, which turns to be 0.619485. Plug C5 into the function to get negative 0.00048. This value can be rounded down to 4 decimal zeros, which means we already have the first root at 0.619485. In the graph, we have identified x1 near the origin. Let's then locate the second root. From the earlier graph, we have the second root still on the positive side of the number line, but a little farther from the origin. The second root is located between x of 1 and 2. However, since the curve rises, we take the left limit as 1 with a negative sign and the right limit as 2 with a positive sign. Place the limits of 1 and 2, and FA is negative 0.28172, with FB as 1.389056. These values are known from the initial values computed earlier. C then uses these values and comes as 1.168615. F of C is then e raised to 1.168615 less 3 of 1.168615, which turns to be negative 0.28831. Let's redo another set of iteration, starting with FC sign check. It is negative, so C replaces the negative limit, which is A. B remains as 2, so FA is then computed as negative 0.28831, while FB remains to be 1.389056. C is again computed from the computed parameters and turns out as 1.311517. Use this to find f of C, which is then negative 0.22275. The third iteration is the same. The sign of FC is again negative, So A now becomes 1.311517. B is still 2. FA is negative 0.22275 and FB is 1.389056. Use these to compute for C, which is computed as 1.40665. This value back to the function and get f of C as negative 0.13768. Continue with the fourth iteration. The sign of FC is still negative, so C replaces A, and B is still 2. F of A is then negative 0.13768, while FB stays at 1.389056. C is computed as 1.46017, while f of C becomes negative 0.07382, already the first decimal zero. The next iteration starts with a negative FC, so A becomes 1.46017, and B is still 2. FA is then negative 0.07382, and FB is still 1.389056. The new C is computed as 1.487411. Plug this into the function and have f of C as negative 0.03661. Do the same procedure in the sixth iteration. FC is still negative, so C replaces A and B is retained as 2. F of A is then negative 0.03661 and FB is still 1.389056. C is computed as 1.500574. Use this to solve for FC, which then is negative 0.01746. We are now on the seventh iteration, and let's see if we can have this as the last. FC is still negative, so the new A is 1.500574. B is retained as 2, so FA is negative 0.01746, and FB is 1.389056. C is computed as 1.506773, and using these to the function, FC comes out as negative 0.00817. We have progressed to double zero, but we are still iterations away to 4 decimal zeros. Do the same procedure on the 8th iteration. FC is still negative, so A now is 1.506773. B is still 2, and f of A is negative 0.00817. FB remains the same. Compute for C. This time, it turns out as 1.509658. F of C is then computed from this value and results to negative 0.00379. A few more iterations to the end. The ninth iteration still have A changed into 1.509658 because the sign of FC is still negative. B is still the same. FA then becomes negative 0.00379, but FB also remains the same. C is computed from the function and the new values of A, B, FA, and FB, and turns to be 1.510993. Substitute this new C into the function and get negative 0.00175. Proceed with the same procedure for the 10th iteration, where having a negative FC means A becomes 1.510993 and B stays the same. FA is then negative 0.00175 and FB is 1.389056. C10 is computed to be 1.511608, and plugging this value into the function gives FC as negative 0.00081. Probably one more iteration to reach the required accuracy. FC is still negative, so A is now 1.511608 and B is 2. FA is taken as negative 0.00081 and B is still 1.389056. C is computed from these values as 1.511892, where using these into the function provides negative 0.00037. This time, FC can be rounded down to 4 decimal zeros, so this ends the iteration, and the second root is computed as 1.511892. Checking on the graph, we have the second root within the interval of 1 and 2.